things, and certainly would encourage any questions that you have. And I think we're going to wait till the end for those. Otherwise, Mike will interject and let me know if we have something pressing to discuss. So as Mike said, my name is Brian Jennison. I'm with Valent Air Management Systems based out of Minneapolis. And the topic today is best practices for DOAS design. Here's the agenda of what I'm planning to talk about today. First, we're going to define DOAS. Our industry has a lot of fun acronyms, so we're going to dive into what that means. We'll talk about the standards that apply to DOAS equipment, and then we'll get into system design and equipment design considerations and the important factors to consider when laying out that equipment. And then at the very end, I'll give a brief Valent product overview. We'll start by defining dedicated outdoor air systems. So what is DOAS exactly? Well, ASHRAE defines a DOAS system as you can read there yourselves, and then it also defines a DOAS unit. So two different things, a system and a unit. A DOAS unit is a part of a DOAS system. And so typically you're talking about high amounts of outside air. And ASHRAE defines a DOAS unit as dehumidifying 100% outside air. So that's typically what most people think of when they think of a DOAS unit. During my talk today, I'm going to expand that definition just a little bit. And I'm going to call a DOAS unit anything delivering high amounts of outside air. And it's typically done with package refrigeration, although it doesn't have to be. The key difference here that I want to point out is that a typical package rooftop unit is designed for 25% outside air or less. And so that's really the key distinction. A DOAS unit, in my definition, can accommodate up to 100% outside air. And it is certainly capable of operating down to 0%, like a recirc mode, for example. But that's really the key distinction between a package rooftop unit and a DOAS unit is anything above 25% outside air, that's really in the realm of a DOAS unit, right? Package rooftop units just aren't designed to handle that much outside air. So going forward, that's going to be what I'm talking about is anything higher than 25% outside air, we're going to call a DOAS unit. So why ventilate with a DOAS unit? Why not just use a package rooftop? Well, there's a lot of reasons. Using a unit that's specifically designed to handle that outside air, you're going to have much better indoor air quality because bringing in more outside air leads to better air quality, right? You're replacing the dirty air, you're exhausting that, and you're bringing in fresh outside air. So a DOAS unit brings in fresh outside air, which allows you to meet those ventilation code requirements, right? A lot of buildings, depending on occupancy, will have requirements for the amount of outside air that you need to bring into that space. So it's a requirement. And then DOAS units, because you're decoupling that sensible and latent load in the space and you're bringing in outside air, you're able to much better control the humidity in the space because you're tempering that outside air and it's not mixing your unit size to dehumidify that full amount of outside air. So you have much better humidity control. And then reduce energy use. Again, that decoupling of your sensible and latent loads in the space drastically reduces that energy use because you're not having to dehumidify and cool a bunch of recirculated mixed air. All you're doing is dehumidifying that outside air. And then it allows you to do some interesting design things like pair it with certain systems that really don't have a dedicated outside air delivery system. So for example, VRF, chilled beams, right? So it allows you to pair it with those technologies and still meet the ventilation requirements of that space. And so a lot of different advantages for using a DOAS unit. If we look at this table that shows different humidity ranges and various growth patterns for different agents such as bacteria, fungi, etc. And this is kind of it illustrates the best growth areas for these different agents. And ASHRAE recommends about 30 to 60% humidity as what they call the optimal zone. So that's usually where we target our delivery of supply air to be in that 30 to 60% range. So I wanted to illustrate this because a lot of people think of relative humidities when they're doing their designs, And it's good to take a moment just to think about why we're typically designing in that 30 to 60% range. This is one of those factors, right? We want to minimize growth of certain agents like bacteria. And this is why humidification and dehumidification, right? We don't want it too dry. We also don't want it too humid. So a DOAS unit helps keep us in that optimal humidity range for occupant health. So some relevant standards to DOAS units, I'm going to talk about three of them today. The first one's ASHRAE 62.1, and that's the ventilation standard, right? We're all probably fairly familiar with that standard. That dictates how much ventilation area you need to bring into a space based on the building type, occupancy, different criteria like that. So that standard certainly applies to DOAS units. The other one's ASHRAE 90.1, which is an energy standard. And again, this is also very important, as we'll talk about later. When you design a DOAS unit, right, you think about bringing in more outside air, you have to heat and cool and dehumidify that air, right? And that takes a lot of energy. So, think about how do we minimize that energy use? And DOAS units have certain technologies that aid in that because we have to meet certain energy efficiency requirements. This third standard you might not be as familiar with, certainly not as popular as the first two standards, but it's HRI standard 920. And that is the moisture removal efficiency standard, and it applies to DOAS units. And so essentially this standard was developed just for DOAS units. And it's a little bit different than HRI 340-360, which you're probably familiar with. And the key differentiator is that HRI 920 is a measure of moisture removal effectiveness. So in a submittal, you might see MRE and ISMRE, right? You're probably used to seeing EER and IEER, but the 920 standard efficiency metric is ISMRE, which is basically moisture removal over energy input. So this table is a contrast of the two, and you can just see the differences there. And I'll highlight that the key difference really when you're rating the equipment is it now dictates a certain wet bulb temperature that's paired with your dry bulb in those 4 test conditions. So we're really looking at how does the unit operate at these different conditions, and how good of a job does it do of removing moisture from the air? Because that's really a key metric for DOAS units, because they're dealing with such large volumes of outside air that dehumidification is really important. Okay, so we've set the framework for what a DOAS unit is, and now let's dive into some system considerations at a more general level. So right here, we've got a psychrometric chart, which I'm sure we're all familiar with. But the key question often comes up when I'm laying out a DOAS system: what design day should I use, right? ASHRAE has various design days available to choose from. The most common would be your dry bulb design day. But there are others. There's a dehumidification design day, and a few others that are similar. But how do we know which one to use, right? So the first one, cooling design day or dry bulb design day. And in this example, I'm using Minneapolis because that's where I'm from. So bear with me on that. But 9173.5. Okay, that's a pretty common design day here. The other one we could choose from would be the dehumidification design day. And you'll notice that the dry bulb temperature is lower, but the humidity is greater. So the absolute humidity at state point 2 is much greater. Okay, so well, which one should we use? Let's just take a look at the psychrometric process. If we cool down with let's just choose a compressor size. Let's say this is a 10-ton compressor, right? So we're going to cool down to about 50 degrees. And then our space is going to naturally heat back up based on the given loads in the space. We're going to sit at 75, 50% RH. So great. We're at a good set point. That humidity is in the right range. Great. So we'll call that a 10-ton system. Well, what if we use that same 10-ton system and we apply it to state point 2? Well, in that case, we're only going to be able to cool and dehumidify down to 55 degrees because that state point 2 has a much higher enthalpy than state point 1, where there's more grains per pound. And so in that case, we're going to float back up, with a sensible heat ratio. We're going to get to 75, but our humidity is going to be much greater, 58%. So depending on the application, that may or may not be okay. And so those are the things we need to think about. And in most cases, that dehumidification design day is going to be your worst case scenario in terms of enthalpy, right? So that's really the lesson here is if you're laying out a unit with delivering high amounts of outside air, you really need to look at that dehumidification design day. And I know a lot of times we're kind of going fast. We're going to pull that dry bulb design day because we remember it. It's used for a lot of different things. But this is a really critical differentiator for a DOAS unit is you have to look at that dehumidification design day. Otherwise, your unit might be short on capacity on that design day. Well, what about off-peak days, right? Most of the year, we're not running at full design, and it's very few hours that we're at the peak design day. So what about a day where, let's say it's a little bit cooler, but the humidity is really high? I'm thinking, this is a perfect example. Springtime, it doesn't get too hot, but it can be very muggy. Sometimes even in the summer, we get some muggy, humid days, but it doesn't get that hot. So what about those days? So I've plotted that point on that blue dot, and then we've got our space window there in green. So that's kind of our target. And let's say, okay, let's try economizer mode. Well, that's not going to get us there, right? We can't just bring in that air to the space. We're going to lose the humidity of the space. Well, let's try a cooling mode. We're not going to quite get to that window, right? So we're going to have to overcool first of all, and then that natural heat gain from the space loads, we're still not going to quite get there. So it's going to feel a little cold and clammy in the space. So it's not optimal. Well, what happens if we have a true dehumidification mode? In this case, we're going to cool down to a lower dew point, and then we're going to have reheat. So there's two red lines. The first red line is a hot gas reheat. And then that second line would be the sensible heat ratio, or getting back to using the space loads to get back into that window. So, it's really important in this case to have components that can modulate, because again, in this condition, we're not going to be running 100%. We're probably running at some modulated down part load condition. So compressor turn down is really important. Condenser fan modulation, hot gas reheat valve modulation. So those are all important things to think about. Your DOAS unit, or system for that matter, has to be designed to handle those peak days, but it also has to be designed to handle the part load days, be able to modulate your compressors and other components down. So I've been talking a lot about sensible heat ratio, and I'd like to show an example here of why that's important. And specifically, you might have a building with a lot of different zones or spaces. And how do you choose what your design is if you've got multiple spaces, your system serving multiple spaces like that? So in this example, again, I'm putting up our target window here. And we've just chosen an outside air state point as an example. So what we'll do is we'll look at three spaces. And in this space, we got a sensible heat ratio of 1. So basically that's all just sensible heat being added. There's no latent loads in the space. So in that case, if we cool down to 55, we're gonna get right back into that zone. Well, what happens if our sensible heat ratio changes, right? What if we add more of a latent load in the space? Well, then we're going to have to dehumidify down further, right? Our off coil temperature is going to have to be lower because there's more of an angle to get back into that space, into that green zone. So that would be a classroom. What if we looked at an auditorium with a higher latent load? We're going to have to go even further with our dew point temperature. So that would be like the worst case scenario of these three, right? So much higher latent load requires a much lower dew point. So if we're designing a system to serve all of these spaces, what we need to do is design it for the worst case scenario because we have to be able to meet the auditorium dew point requirements. And then for the other spaces in the classroom, uh, usually those are served by terminal units, so you could do a little more reheat, but you have to be able to handle the worst case scenario. So this is an important thing to think about is what's your worst case from a load standpoint, right? Both sensible and latent, and then determine what that dew point temperature is that the space needs. Another consideration is how we're going to deliver that ventilation air. So in this example, we've got a couple cartoons of a DOAS unit and then some ductwork and terminal units. And so those are just two configurations, right? There's other systems and things we could look at, but I just put these two examples up just to illustrate a point of, things to think about. Where do you want the DOAS unit to run separately, or do you want the DOAS unit to run together with the terminal units, right? So that will change how you design the system. And do you want to deliver neutral air or cold air to the space, right? So if you're going to have your terminal units reheat the air, that might change how you select your DOAS unit. And it depends on what the space is being used for, occupancy, control methods. So, when you talk about the system, you have to think about the different components and how those are all going to work in concert together. So just to summarize the system design, we want to design around the dehumidification design day. That's going to enable you to properly control the temperature and humidity in the space. And then we also want to pick the optimal dew point, right? We want to see what's our worst case zone. And then we have to design around a dew point that we can supply to that zone that will allow us to control the humidity in that zone. And then proper air distribution and looking at not just the DOAS unit, but all of the DOAS equipment in that system working together. All right, so now we're going to talk about equipment design considerations and more specifically DOAS units in general. So I'll dive into a lot of different topics that we see with DOAS units. So again, I alluded to this earlier, but DOAS units are different than package rooftop units. DOAS units have to handle a wide range of entering conditions. And this psychrometric chart I plotted here, I think I pulled it from ASHRAE, but it shows Minneapolis bin data, and you can see there's a huge spread of outdoor air conditions, right? And Toronto's very similar. We have hot summers and cold winters. This obviously will change depending on which part of the country or world you're in. San Diego, they don't have quite as big of a spread, so lucky them. But in these places where we have really drastic temperature and humidity swings throughout the year, this could be a challenge. And as I mentioned, a package rooftop unit, because it's bringing in so little outside air, that range that the unit has to operate in is much, much smaller. And those units do a great job, but only in that range. That's what really they're designed for. So again, a DOAS unit has to be able to handle all of those state points. I pulled this from the ASHRAE design guide, but essentially it says that handling outside air up to 100% is very difficult to accomplish with off-the-shelf package equipment. And I might be so bold as to say it's hardly possible to do that. ASHRAE is a little nicer to the package rooftop units than I would be, but this ASHRAE is certainly on board with this notion that we need to do things a little bit differently for a DOAS unit than we would for a package rooftop unit. So I'm going to talk about just a few fundamental features and some different design considerations with the DOAS unit. I'll dive into the details here. I've got a couple pictures up, and one of the key differences with the DOAS unit is the casing and the cabinet construction. And that might not be the first thing you think about when you think of a DOAS unit, but it is critically important. It all starts with the foundation of how you build the product. So one of the fundamental features is an ejected foam panel. So there's two things that's going to do. One, it's going to minimize the amount of heat loss or energy transfer to the ambient, right? If you're going to bring in outside air and temper it, you don't want to be forfeiting all that work, by leaking the energy to the outdoors again, right? That's lost work that you're doing. So you want to have a really nicely insulated cabinet to keep everything where it's supposed to be and not lose energy. The other thing that injected foam does is it adds a lot of rigidity to the panel and it minimizes that flexing, right? So when you pull air through the unit, sometimes the casing will flex and air leaks out. That injected foam does a nice job of preventing a lot of that. And so again, minimizing energy loss. If you're leaking air to the outside, that's lost energy because you're tempering the air and now it's leaking. So you want to have a really solid cabinet. What some package rooftop probably more so, but even some DOAS unit manufacturers are using what we call foam board. That's the picture on the bottom. And it's still an R13, but you'll see that it has some cavities and holes cut out, and it doesn't fill all of the spaces in the panel. So you get a little more leakage and energy loss through that particular insulation. So just something to consider when you're laying out your units. And then we want to be able to have our coils, DX or chilled water, whatever's pulling humidity out needs to be sized appropriately. So a package rooftop unit, you're probably looking at a 2-3 roll coil maybe. DOAS units, because we're dehumidifying, we need to have proper surface areas and proper coil depths to ensure, 4 or 6 rows probably to ensure that we are dehumidifying that air. And then your heating components, similarly, dealing with very low temperatures and large delta Ts, those need to be sized appropriately for large capacity electric heater, for example, or furnace. And then also modulation is important. Remember, we talked about modulating those components to meet those part load days. So high turn down is really important. If you got a 3-to-1 turn down furnace, let's say you've got a 60-degree delta T, well, that means your minimum turn down is 20 degrees. And there's a lot of times during the year where you might only need, let's say, a few degrees of heat, right? In the shoulder seasons, you don't need 20 degrees. You're going to be turning your furnace on and off, and that leads to a lot of temperature swings in the space. So, you're going to want 10-to-1, 12, 16-to-1 turn down on your furnace, for example, or a fully modulating electric heater, right? Electric heat or air source heat pump, whatever it is, you want to be able to fully modulate your heat, especially. So some other fundamental features, again, we mentioned the modulating components. Also, control sequences are really important, and we'll talk about that a little later too, but making sure you've got separate heating, cooling, and dehumidification modes is critical. And energy recovery, you know, I've got some other slides to talk about that, but that is another critical part of DOAS units because you're bringing in outside air. You want to be able to pre-cool or preheat that air, and that makes a big difference. So I mentioned that most DOAS units that we see have some sort of refrigeration, whether it's a heat pump or just packaged DX. And that's a critical part of the system. One thing I'd like to talk about is the hot gas reheat, because in dehumidification mode, this hot gas reheat allows the supply temperature to be brought off of saturation. So we don't want to provide, in most cases, we don't want to provide 55-degree saturated air to the space. That can feel very cold and clammy. It's not very comfortable. And so we use hot gas reheat as a means to reheat that air to a more comfortable point. And it's really just recycled energy from the compressor. We're using hot gas from the refrigeration system. Instead of rejecting that heat to the ambient, we're using that heat, injecting it back into the supply air. And so it's a really good reheat control method, and really good for dew point control. There is some confusion in the industry about hot gas reheat and hot gas bypass. So hot gas reheat is a means to reheat the supply air. Hot gas bypass is an older technology that's used to modulate the capacity of your compressors and really your DX coil. So you're essentially putting a false load on your evaporator coil, your DX coil. And that's the way you're modulating capacity. So you're essentially doing negative work just to modulate capacity. So it's not that efficient at all. And by and large, this technology has fallen to the wayside due to the rise of the modulating compressor. So we rarely will see this, and it's again sort of a antiquated technology. There's another bypass that gets thrown around, and that would be evaporator coil bypass. That's another way to control your capacity, but typically we don't see that on DOAS units because what you're doing is when you bypass the evaporator coil, you're mixing air downstream of it, and so it's not a very good method of controlling humidity because you're still keeping humidity in that mixed air. So when we have a DX coil, we want to put all of our air through that DX coil, dehumidify to a certain dew point, and then reheat. So it gives you much better control. So don't be confused when you see hot gas reheat, hot gas bypass, DX coil bypass. Those are all very different methods. But really the key one to remember is just hot gas reheat is a good thing. Most manufacturers are doing that. Hot gas bypass and DX coil bypass are far less common. So compressor modulation, I've mentioned that's an important thing many times here. In case you're unfamiliar with the way a compressor works, this is a scroll compressor. There are different kinds of compressors. This is just a scroll. This is one of the most common types of compressors, I'll say, in the DOAS world right now. And the graphic that I've got there is actually a digital scroll compressor. And the industry is moving away from these mostly because they're not quite as efficient as an inverter compressor. And you'll see that for a digital compressor, the way it controls the capacity is it will unload or disengage. The scroll disengages every so often. You'll see the blue part rises. So that's really how it modulates, and it disengages every so often. So it's great control. The reason that we're seeing more inverter compressors is that for two reasons. One, they're much quieter. The chart on the left is, I would say, not a very scientific plot, but it just illustrates the sound profiles of the two compressors, right? Digitals, when they load and unload, they're still pretty loud and noisy. Because an inverter scroll has a VFD on it, it can modulate fully. So it basically lowers its own scrolling speed or increases, and that's how it modulates. The other main reason I would say that we're seeing more inverter compressors is the efficiency. The Department of Energy has new requirements as of this calendar year for units, and that drove many manufacturers towards inverter compressors because they're much more efficient at part load. And if you think about your DOAS unit, most of the time during the year, it's going to be at some part load condition. So actually, a digital is a little bit more efficient. You'll see at 100%. But again, at all part load conditions, an inverter compressor is way more efficient. So that's really the reason why we're seeing more inverter compressors, is low sound and much more efficient.
Brian, we had a question come in back to bypass with DX coil air. Zane had called out that sometimes mixing conditions after the DX coil with bypass is better than having all the air through the DX coil. And I think your point was more towards dehumidification strategies, but I'll let you speak to that quickly.
Right. Yeah. So there may be times when, I'm thinking more along the lines of like if your unit's purely in cooling mode, that might be beneficial to not not cool all of the air. So maybe some mixing downstream would be advantageous. But if you're in a purely dehumidification mode, where you're trying to take air from one enthalpy and drop that enthalpy down, or drop the dew point, it's harder to control your dew point if you're only dehumidifying part of the air. And certainly, I know it happens where people will bypass that DX coil, And in some cases, it may not be a big deal because your space might not have super tight humidity requirements or tolerances, right? But if you're trying to dial in your dew point and control what that humidity in the space is, bypassing some air around the DX coil does not help your cause at all.
Thanks very much.
Sure. All right, so condenser fans is another part of that refrigeration system. And I'll just highlight briefly here that a lot of manufacturers are moving towards what we call performance blades. And you'll see a picture in the bottom left. And the industry standard for many years has been what I'll call a paddle blade condenser fan. Those are actually pretty noisy. We've got sort of a relative scale of decibels, you know, from conversation up to a chainsaw. And what I'll say the industry standard for many years, the paddle condenser fan is about 80 decibels. Those performance blade condenser fans are much quieter now. And so, you know, sound isn't really going to, it's not going to apply to every job. You know, some jobs sound's not a big deal, but it seems like more and more these days, sound's becoming a big deal. And people want quieter and quieter equipment. So I mentioned that the inverter compressor is much quieter, and most manufacturers have moved over to the inverter compressor. There's a trend here as well where we're seeing more of these performance blade condenser fans. So that's another important thing to think about is what are the sound requirements of this particular building and surrounding buildings, and how quiet do I want my equipment to be? Now, I mentioned controls was another important key factor in DOAS units, and so I'll just highlight some of the controls that we have to think about. So obviously we have our temperature control modes, right? Do we want the unit to be heating or cooling? We also have dehumidification, and so we want to control our hot gas reheat valve as well. We might have energy recovery. Two most common would be wheels or plates. And then ventilation control. We want to control our fans. There's a lot of different fan control options, and our dampers, right? So we want to control our outside air damper that can help us bring in more or less outside air. So all of these components have to be working in concert together. So it's important to think about what kind of control modes and methods do we want? And there's a lot to choose from. So just a reminder, cooling mode is different than dehumidification mode. Really cooling, all we're trying to do is meet our discharge air temperature set point, or it might be a space temperature set point, but you know, that's really it. And sometimes you have to control multiple compressors if it's some part load condition, and your trigger is either discharge air or space air temperature set point. Dehumidification is a little more complex, where you have to look at both the dry bulb temperature and the dew point. So you're using hot gas reheat in that case, and this can be triggered by a variety of factors. Typically, you're looking at outside air dew point if you want to be proactive. You could also look at your inside conditions as well, or a combination of both. As a reminder, this is about how we divide up the psychrometric chart to determine what mode we're in. And think about heating mode, that's pretty obvious. Cooling mode. Once you get above that blue line, you have a pretty significant amount of both sensible and latent heat. And again, you know, there's different things you can look at to trigger the dehumidification mode, right? You might look at the space conditions, or return air, especially if you're dealing with a lot of recirculated air in your unit. If you have a unit that's supplying primarily outside air, let's say 100%, then you're probably going to want to look at the outside air conditions, right? Because if you're going to wait to look at the space conditions, you might lose control of the space and have to play catch up. But if you look at the outside air, that'll help you maintain humidity in the space. And then there's different modes, right? Occupied versus unoccupied, and how do you handle those? So those are all important things to think about. So energy recovery, why is this important? Well, again, we looked at that bin data, and that's really the zone we want to try to operate in. That makes it a lot easier. It also helps us save energy. So we want to increase our operational efficiency by reducing the amount of heating and cooling we have to do with our mechanical systems. It also can reduce first cost. If we add energy recovery, that means that we can reduce the size of our heating and cooling equipment sometimes. Makes our unit more energy efficient and can meet that ASHRAE standard 90.1, which requires energy recovery in certain cases. So there are a lot of different energy recovery types out there. I'm sure you've seen them around. There's cores, wheels, heat pipes, runaround coils. For DOAS units, there's really two, what I'll say are most common types of energy recovery. That's wheels and cores. So wheels are the most popular by far. Basically, they rotate in place, and they have a motor and a wheel, or I'm sorry, a motor and a belt that drives the wheel. And there's two main kinds. There's an aluminum wheel and a polymer wheel. They have fairly similar performance. They're just a little bit different in terms of their construction. And so if you're unfamiliar with the way a wheel works, again, air goes through one side, that would be your supply air. And then on the other side of the wheel is your return and exhaust air. So in the summertime, for example, your hot, humid air dumps some of its heat and moisture to the return air stream before it gets ejected, which thereby will pre-cool and pre-dehumidify your supply air. So we're just transferring energy from one air stream to the other. The advantages of a wheel is it's very effective. Typically 75 to 80% effectiveness. And so that's really effective. And it's a proven technology, very thin profile, doesn't take up a lot of space. So that's probably the main reasons why it's been such a popular option. There are some disadvantages though, in that it has moving parts. It has a motor and a belt, and so those need to be maintained. And it also has a relatively high leakage rate, in which some cases it doesn't matter, right? If it's just an office building, 5%, 10% leakage rate's not a huge deal. But if you're talking about a lab exhaust, for example, that might not be acceptable for the application. Another consideration when looking at a wheel is some manufacturers we've seen will short circuit the outside air or part of the outside air around that wheel. And the reason they'll do that is to get a smaller box size, essentially. But what that does is it sacrifices the amount of energy recovery that you're doing with that wheel. So that means your downstream systems, your heating equipment, your cooling equipment, they have to pick up more of that load because you're not doing as much energy recovery. So this is another important thing to think about is, do you want a wheel that's sized for the full amount of outside air, or do you want a smaller wheel that's not going to do quite as much energy recovery? And typically, I would recommend doing that, the full-sized wheel that can handle outside air, the full amount of outside air. So the other main type of energy recovery is that enthalpy core. And the advantages really are, it's really low cross-contamination. It works in the same principles. It's just a little bit different in the way it's configured. You'll see it's a cross flow, so that it looks like the air mixes in the middle, but it really doesn't touch because there are plates that separate the air. And so in this case, same principle. You've got your outside air in summertime, basically dumping its heat and moisture to the exhaust airstream. And so just another way to pre-cool or preheat the air, depending on which time of year you're in. And the core is still effective. It's 50 to 65%, which still meets the ASHRAE requirements and the code requirements, but not quite as effective as a wheel. And the big advantage it has over a wheel is that there are no moving parts. So it doesn't really need to be maintained as much as a wheel. So this is an attractive option for applications where you might not have a dedicated maintenance staff, for example. The polymer medias are actually frost tolerant, and they have antimicrobial coating, and you could wash them with water. So they're pretty robust. And then the cross-contamination is really low. So it's less than 1% cross-contamination versus a wheel, which you're going to be, 5%, 10%, depending on the airflow balances there. So much lower cross-contamination. The enthalpy core disadvantages is that it's bigger than a wheel. If you choose a paper media, that can be damaged by frost or water. And again, it's less effective. It also has a higher pressure drop. So there are pros and cons depending on what you pick. But those are really the two most common types of energy recovery. So just to wrap up this section, when we're laying out DOAS equipment, there's some important considerations. One, we want to make sure we are using a good foam injected cabinet and robust components that have really good modulation. So compressor modulation, hot gas reheat, whatever our heating type is, we want to make sure we can fully modulate those components. And then the control modes we select are equally important, the heating, cooling, dehumidification modes. And then within those modes, what type of control methods are we using to control our fans, dampers, those components individually, set points? All of those things are very important. And then energy recovery. Not every application is going to lend itself well to energy recovery, depending on how the ductwork's laid out, the needs of the space. But if you can design energy recovery, and in some cases it's required, looking at a wheel versus an enthalpy core, those are all important things to consider as far as the operation of the unit goes. So one final slide here, just to talk about Valent a little bit. Valent is a DOAS unit manufacturer, and we've got several different cabinet sizes there. We go from 500 to 18,000 CFM, and we do package DX, air source heat pumps, chilled water, and on the heating side, we do furnaces, electric heaters, hot water, steam coils, again, air source heat pumps, and we can provide all of our units with or without energy recovery. So that's all the material I have today. Thank you for your time. And at this point, we'll open it up for questions.
Thanks, Brian. Appreciate it. We did have a question come in regarding pressure drop between cores and wheels. I commented that, there's a greater pressure drop with cores, generally about 0.4 inches across a wheel and up to 1 inch, depending on the type of core you might have. But I don't know if you have anything more you want to add to that, Brian?
Yeah, I would say that's generally right. The core is going to have, for a given face area, the core is going to have a higher pressure drop. What that really translates to is when we're talking about fixed cabinet sizes, what manufacturers will do is rather than have such a, that's a pretty stark contrast in pressure drop. So they'll basically just increase the size of that core to get the pressure drop in a more normal range. But that limits the amount of airflow that you can put through the core. So it's some combination of having a bigger core versus lower airflow allowed through that core. But you're right, Mike, that's generally what we're seeing is, up to an inch or even more sometimes for a core for a given airflow. A wheel is significantly less than that.
Thanks, Brian. Another question came in. What is the best practice to control the DOAS unit used with a terminal unit of the VRF system?
Great question. We're seeing a lot more of this, especially as VRF keeps rolling along. Probably, I don't know if there's a best answer. There's rarely a best answer for anything that applies to all situations, but I would say the most common one that I see is for the duct static pressure control. That's how you control your supply fan. So as those terminal units open and close their dampers, that gets basically fed back in the value of duct static pressure. So that's what our unit would look at, and then it would modulate the fans accordingly, right? So do we need to supply more or less air depending on how many terminal units are delivering air to their spaces? I've seen it done other ways, but I would say if you have a terminal unit or multiple terminal units feeding multiple zones, that duct static pressure is the most common.
Perfect. Thanks, Brian. Any other questions? Please feel free to add it in the chat.
Otherwise, I guess one thing to piggyback on that, Mike, maybe this was the other part of the question that I didn't pick up on, but that would be supply fan control. If you're talking about temperature control, what I've seen most commonly, if you have terminal units, the temperature control is set to a certain discharge set point. And usually that's, 50 to 55 degrees. And so the DOAS unit's going to control to that particular set point and then deliver that, let's call it 55-degree air to the terminal units. And then from there, the terminal units will have some kind of a reheat, whether that's hot water or whatever. But that would be another typical control sequence.
Great. Thanks very much, Brian. Appreciate it. I think we'll probably leave the session here for today. Thank you so much, everybody, for joining us. Brian, that was exceptionally informative. I really appreciate your time today. And I really appreciate everybody taking the time to join in our continuing education session today. If there are any further follow-up questions, please don't hesitate to reach out to your local Odell office, and we will make sure that all of those questions or requests are taken care of. Thanks very much.
Thanks, everyone.
Take care.